Before watching this video, make sure that you've watched the TED Ed talk, How the Koenigsberg Bridge Problem Changed Mathematics, to give us context for what we're going to talk about in terms of Euler paths and Euler circuits. An Euler path in a graph is first of all a path, which was a definition that came up in our previous lesson, that uses every edge of the graph exactly once. So remember, a path, first of all, means that it goes along the sequence of edges that are connected in the graph. And to be a path, not only do you have to be going along the sequence of edges in the graph, but you can't use any edge more than one time. So you can't backtrack over the same edge. Now, to have the additional idea of being an Euler path, you have to be a path and every edge must be used exactly once. An Euler circuit in a graph is a circuit. Remember that a circuit is a path that begins and ends at the same vertex. So not only is it a circuit, but it also must use every edge of the graph exactly once. Consider the graph given here. We've got vertex A, vertex B, C, D, E, and F. And we're asked if this sequence of vertices is an Euler circuit. So let's first consider, is this even a circuit? And then if it is, we can ask ourselves, does it meet the additional criteria to be an Euler circuit? Okay, so we're going to start at A, and then we're going to go along an edge to B. There is such an edge. From B, we're then going to go to C along this edge. Now from C, we then go to E along this edge. And then from E, we go to A. Okay. Now, why this is a circuit? Because it's a walk. It's also a path because it never crosses over the same edge more than one time. And it's a circuit because it begins and in the same place on top of all of that. It is a circuit, but it is not an Euler circuit. The reason it's a circuit but not an Euler circuit is because notice we don't use the edges that I'm going to highlight here in pink. This edge isn't used, nor is this, nor is this, nor is this along the sequence of vertices. And to be an Euler circuit, you've got to use every edge. So since these edges weren't used, this is not an Euler circuit. Next, we're asked in general, does this graph have an Euler circuit? Let's try to find one, if there is. So let's say we just start at A. Suppose from A we then go to B. Now there's one thing that I want to draw our attention to. This graph does not have an Euler circuit. And the reason that I'll try to show here is if we start at A, eventually we would have to come back to A through one of the two remaining edges. So say eventually we went through other vertices, but eventually we started coming back through this vertice, and we're at A again. Since it has to be an Euler circuit, it has to use every edge. We already used this edge of A and this edge of A, but we'd still have to use this edge of A eventually later. But then do you see that there's no other edge that we could come back through A without repeating an edge? And to be an Euler circuit, you can only use each edge exactly once, so we couldn't repeat. So since our starting point has an odd vertex here, or a vertex of odd degree, or any vertex has a vertex of odd degree, it can't be an Euler circuit because you've got to have an even degree to be able to pass through and then come back without using the same edge more than one time. So we would say here that no, this does not have an Euler circuit. And the idea that we used in the last example is clarified by this rule. Suppose that you start with a connected graph. Remember, connected is a definition from our previous section. Then, if the graph has an Euler circuit, so if there is one, then each vertex of the graph has to have an even degree. And then we also have the reverse of that. If you know each vertex of the graph has an even degree, then you're guaranteed it has an Euler circuit. So we can, by counting the degrees of each vertice and seeing if they are all even, know whether a graph has an Euler circuit or not. Consider this graph. So we've got vertice here, vertice here, vertice here, vertice here, and the connecting edges. And we are asked, does it have an Euler circuit? Now in this case, we're just asked, does it exist? It's not really asking us yet in this example to find it. So if you're asked if an Euler circuit exists, you should immediately ask yourself the question, are all the vertices of the graph of even degree? And remember, even is just mean if you count the degree of the vertice, it would be something like 2, 4, 6, 8, 10, 12, 14, and continuing on through the even numbers. Any of those are a possibility. So let's just label the degree of each of these vertices off to the side of each vertex. This vertex has 2 edges, so it's degree 2. This vertex has 1, 2, 3 edges, so it's degree 3. And actually at this point, we don't need to continue any further. We have found one vertex that is odd degree, which means immediately no. So that means that there is not an Euler circuit. So it's really important to first identify, based on these 2 rules, if an Euler circuit exists, because if it doesn't exist, you don't want to spend time looking for it. And to determine if it exists, it just comes down to finding the degree of each vertice and ensuring they're all even. Same question for this graph. For the graph, you're supposed to determine if there is an Euler circuit. I recommend you pause the video and just determine at this point, are we guaranteed to have one exist? Not find it, but just identify if it exists based on our previous criteria. To know whether an Euler circuit exists, we would first want to find, are the degrees of every vertex even? If so, then there is an Euler circuit. So let's just write down the degrees of each of these vertices. This is degree 2, degree 4, vertex D is also degree 4, degree 4, degree 2, Since every vertex in the graph is even degreed, this means that we are guaranteed that it has an Euler circuit. So we know one exists, and later we're going to go through how to actually find the Euler circuit that exists. We're asked here, beginning and ending at the same place, is it possible to trace the pattern shown in the figure here without lifting your pencil off the page and without tracing over any of the any part of the pattern more than once? While there is many ways to solve this problem, one way is to turn this image into a graph and then rephrase the question in terms of, does that graph have an Euler circuit? Because to say that without lifting the pencil off the page, that just means go along the allowable edges. And we don't want to trace over any part of the pattern more than once. So we want to begin and end in the same place. That's the idea that doesn't lift the pencil off the page. That's the idea of a circuit. And without tracing over more than once, that's the idea of an Euler circuit. So for the graph, at the corners we can give each of the corners a vertex. And now we can represent this figure by a graph. Okay. And we've been able to rephrase these criteria along with the graph to really asking us, is there an Euler circuit for this graph? Okay. This is a question of existence, and to see if an Euler circuit exists, we would just need to see are all of the vertices of even degree. So I'm going to list out the degrees of each of the vertices of this graph. When listing the degrees of each of these vertices, we see that these vertices are all of degree 5, which is odd, which means there is not an Euler circuit for this graph. Since there's not an Euler circuit for this graph, this means that this pattern can't be drawn in the way described. Next, we're going to introduce a concept that will help us be able to actually identify certain Euler circuits. So not only that they exist, but actually write them down. The concept that we next need to learn is the idea of a cut edge. And the reason we're learning this is it's going to be useful in our next example of using a certain algorithm to find Euler circuits in a graph. We define a cut edge in a graph to be an edge whose removal would turn the graph into a disconnected graph. So you start off connected, but if you remove that edge, it would make it disconnected. Let's look at these two graphs. So we've got two separate problems. I'll separate them here with this purple line. So for our first example here, we're supposed to identify any cut edges, and let's highlight the cut edges. Okay, the one that immediately jumps out to me is C and D. Imagine if we erase this edge. Do you see that would give us the two disconnected triangle components? So C and D is a cut edge. We'll list it off to the side. Okay. Let's consider the other edges. Imagine the edge AB was removed. Notice the graph is still connected. Okay. You could eventually get to B by going through C and then to B. So it's still connected, which means AB is not a cut edge. The reason CD is a cut edge is notice if we delete that edge, there's no way to get from A to, for instance, to D. Okay, let's see is if imagine erasing AC, and you can just do this mentally, see that it's still connected, so it's not a cut edge. If we deleted BC, still a connected graph, not a cut edge. We already established CD as a cut edge. If we got rid of D and E, the graph is still connected. E to F, still connected. D to F, still connected. So the only cut edges for this first graph are C and D. Let's turn our attention to the next graph. Now for this example, we want to identify the cut edges. We can go through this systematically, just asking ourselves, if I remove this edge, is the graph still connected? Imagine if we got rid of the edge A to B. This would make the graph disconnected because we'd have a part of the graph A by itself, completely separate from the other part of the graph. That means AB is a cut edge. We'll continue. Imagine if we deleted B to C. It's also a cut edge because now you've got two separate components. If we deleted C to D, it's also a cut edge because now we've got the two separate pieces. C to E, it's a cut edge because now we still have two different pieces of the graph. Okay. Now if we remove E to F, the graph is still connected, so that's not a cut edge. If we remove F to G, it is also not a cut edge. E to G, not a cut edge, the graph is still connected. However, if we remove E to I, then that is a cut edge because that turns it into two separate pieces. And then I to H would also disconnect the graph. So we found our cut edges for this graph. Now, finding Euler circuits, especially for more complicated graphs, can be a rather lengthy process, and for that reason, sometimes having an algorithm, which is a list of steps, can help you be successful at finding the Euler circuits. One such algorithm is called Fleury's algorithm, and the first thing you need to check before you start going through the algorithm is the graph in question one in which each vertex has even degree? The reason we check that first is because if each vertex has even degree, we know that we have an Euler circuit, and then we go through the steps to actually find the Euler circuit. Step one is you start at any vertex, and then you go along an edge from this vertex to another vertex. So start at a vertex, choose an edge to go along, and then imagine you're removing this from the graph. Now on the revised graph, what we mean by the revised graph is we've removed the edge that we've already crossed. The reason we want to remove these edges is because we know an Euler circuit can't use the edge more than once. So if we've already used it, we kind of remove it from the graph in our mind mentally so that we don't cross it again. Now you choose any edge from this vertex with the condition that you do not use a cut edge. So this is the definition we just reviewed of the revised graph. So the idea is in this new graph, you can choose to go any direction so long as doing so doesn't separate the graph completely. Okay. You remove this edge from the graph, and then you just complete the process until you have used all the edges and returned back to where you started. Let's see this in work in our next example. The question begins by saying find an Euler circuit for the following graph if they exist. So that means before we start writing one down, we want to know if it exists. To do so, we think, are all the vertices of even degree? Let's write out the degrees of each of these vertices next to them. Vertex A is degree 2, vertex B is degree 2, E is degree 4 because there's 4 edges coming from it, C is degree 2, D is degree 2. Since these are all even degree, we know that this has an Euler circuit. And we are asked to find one, not just say it exists. So we'll begin by starting at A. And it says the arrow shows the direction then go to, so it's saying go along this edge. In the algorithm, it said you could choose any edge that's part of the graph from the point that you chose. So I could go to B or I could go to E. This is just your choice, both work. Let's say I go to B first. So as I go to B, I'm going to write that down, A to B. Remember, part of the algorithm means that you remove that edge. Now for me, I can just kind of erase the edge to help me see that. But if you're working on your pen and paper and it's harder to do that, another way you could think of it is if you draw little X's, that helps remind you that you already crossed there. Now that we're at B, I only have one choice because I can't go back to A because that would be reusing an edge, but I can go to E. So I'm next going to go to E. Since I used it, I'll just cross it out so I don't use it again. Now E has multiple choices. I can't go back to A because if I do, there's no other place to go after going back to A, and then I won't have used all of the edges. Now, as we consider should we go to D or E, we need to ask ourselves if we go along either of them and we remove that edge, would that make the graph disconnected? In both cases, it's no, so it's your choice. Let's say we go to C next. So we use this part of the graph. C only has one option, it must go to D. Okay, D must go to E, there's only one choice remaining for it. And then E must go to A. And 1, we know we check to see if it's a circuit, it better at least begin and end in the same place. Is it an Euler circuit? Well, it's used every edge only one time, and we haven't missed anything. So let's just verify A to B, B to E, E to C, C to D, D to E, E to A. So this is an Euler circuit. Now there are many Euler circuits for this graph. This is just one example. If you want to find more on your own, feel free to take a picture of it and send it to me through Canvas message, and I'd be happy to check your work. The instructions are the same for this graph. If an Euler circuit exists, find it. So why don't you take a moment, pause the video now, identify first does an Euler circuit exist? If so, why? And then if not, why not? And if it does exist, find it. Pause the video and unpause when you're ready to check your answer. Remember, before you start trying to find an Euler circuit, you first need to convince yourself it exists. I always like to begin by just labeling the degrees of each vertex. So vertex A is degree 3, vertex B is degree 3, and actually I don't need to even label the other degrees of the vertices, because remember, if even one of the vertices is odd, there is no Euler circuit. So since A has odd degree, this graph does not have an Euler circuit. Now in this example, we're asked to find the Euler circuit if it exists. To first figure out if it exists, you ask yourself, well, are all the vertices of even degree? Vertex A is degree 2, so good so far. Vertex B is degree 4, C is degree 2, D is also degree 4, E is degree 2, F is degree 2. Since all the vertices are even degree, we know there is an Euler circuit. Okay. Now we're going to take a moment to find the Euler circuit. You could either use the algorithm approach, or you can try to see it and just kind of go through a few options in your mind to see which one fits the idea of an Euler circuit. Let's start at A. You could start anywhere, but just so we're all on the same page, let's start at A. Now remember, from A it says go any direction, so let's just decide to go to, let's say, D next. So write down that we've gone to D. Cross this out so you don't use it again. Remember, to be an Euler circuit, you can't reuse edges. Now at D, remember, you can go anywhere so long as it doesn't disconnect the graph. Let's go to C. Okay. Now C only has one option left. It must go to B. There's only one edge that hasn't already been used from C. Now we would not want to go from B to A, because there's no other place that we can go outside of A, so we never would have accounted for these edges, which would mean it's a circuit but not an Euler circuit. So we can't go directly back to A, but you could go either to E or to F. Let's just go to F. From F, there's only one choice. You've got to go to D, because there's only one edge remaining. Now D only has one edge not being used, so we're forced now to go to E. E only has one choice, you got to go to B. B only has one choice, you've got to go back to A. This is an Euler circuit, and again, make sure if you're saying it's a circuit, it does have to begin and the end in the same place. And since it used every edge exactly once and begins and ends at the same place, it is an Euler circuit. Now there are many other Euler circuits. If you come up with another one, feel free to check it yourself based on the criteria for Euler circuit, or send me a picture of your work and I'd be happy to comment. And that brings us to the end of this section of notes.